All right, so this is going to be called quadratic rates of change, and it's part one, to be continued after this discussion, because there's some interesting concepts that I think you need to hear before you get to a calculus level. I think it's very important that some of these concepts you start considering much sooner than when you dive into that level of study. Everything you're doing right now is foundational, trying to get you there. And they're major concepts and they take time to grasp. And the sooner we start those conversations, the better chance you'll have of coming to some understanding. So let's start with some stuff that we've been working with, that we're familiar with, and dive into some of those concepts. Now, we're also studying trig right now, and trig is all about angles to ratios and ratios to angles. Eventually, in another couple of years, you're going to be talking about rates of change yielding amounts, and those amounts figuring out what their rates of change are. All right, so that's kind of a new comment for you. Here I've made a couple of table values. So if I plug in -2 squared is 4, and -2 times -4 is 8. Got a whole series of numbers here that should look familiar. It's the kind of graphing you should have done in Algebra 1. Plug a number in, see what happens, plot it. So here's what you would have plotted for user-friendly numbers. We've had some experience with that in the last couple of weeks, and hopefully you're not just picking positive numbers, but you're starting to extend your understanding into being curious about different sections of graphs, and you're not going to come to any understanding unless you plug numbers in and work with them. I think that's a fairly safe statement, that if you want to understand the calculations you're looking at, plug numbers in, work with them, gain some feel for the calculation, some numerical feel. So pause the video, look here, see where your patterns are, see what kind of patterns you can see, and we'll talk about them. And then when you're done looking, click back the browser here and we're ready to go. So what am I seeing? I'm seeing y values that are decreasing to a minimum, and then they start increasing. And I'm seeing symmetry in those y values. So I'm seeing a change. If this is about rates of change, then we want to do y2 minus y1 over x2 minus x1. I'm seeing 7 units of change, then I'm seeing 5, then I'm seeing 3, then I'm seeing 1, and then I'm seeing 1, 3, 5. Looks like my changes are changing in some interesting ways. All right, so let's talk about some change over a smaller change in x. Let's let our x only change by a little teeny bit. That's what I get when I square that. And I can see that that number's gone up by 0.04, and I've changed by 0.01. It looks like at x squared, when x is 2, you square it, you get 4, but you also get a change of 4 to 1. Roughly 4 to 1 at that instant. Okay. And we were looking at minus 4x as well, and 2 times -4 is -8, but 2.001 squared is -8.004. This number is smaller than that. So y2 minus y1 is actually a -0.004 divided by 0.001. Huh, that one's going down at 4 to 1. And I think the interplay of numbers here gives us different rates of change at different instants. But it seems like that moment, the rates are opposite. So let's look at it from a graphical standpoint. Here we have x squared, and here we have minus 4x. And at 2, the linear function is going down at 4 to 1. And at 2, the quadratic function is going up at 4 to 1. Okay. Rates of change are going to definitely have an effect on amounts, but let's just say that polynomials are numerical tugs of war. And we got the flag on the rope. And I'll use Rene Descartes. I can't pull Rene Descartes from that position. Let's say that I am up against Rene Descartes. And Rene Descartes is pulling in that direction, and I'm going to be pulling in that direction. Notice I didn't say left or right, because looking at the screen here, I don't know how that's going to project. All right, so I am pulling, Rene Descartes is always pulling at 4 to 1 in that direction. I'm pulling at 4 steps per second in this direction. I don't think this thing's going to move. I think those rates offset each other. Whereas if I'm pulling at 10 to 1 in that direction, Rene's pulling at 4 to 1 in that direction, I think I'm winning. But I think if I'm not pulling at all, Rene's winning. And so we've got this tug of war. But I do know one thing. The rate of change at 2 is 0. Constants, doesn't matter what a constant does to these equations. So this is pulling down, minus 4x, gives me an amount, a negative amount. That's a positive amount. Well, the negative's winning. That's a positive y value. That's a negative y value. That's bigger. My graph is still decreasing until I get to what? Here, where that rate of change is offset by that rate of change. All right, and maybe my y values are continuing to go down until this instant, and then I'm pulling up at a rate faster. Rene's winning. I forgot who Rene is. Rene's the linear, and I'm the quadratic. Sorry, cognitive decline continues, but hopefully I made my point. Now, what have we done algebraically? Let's see. Algebraically, let's go down here. So far, you've learned to put this into graphing form by using minus b over 2a. Okay, minus b, positive 4 over 2 times 1. Lo and behold, what a coincidence. It appears that 2 is the magic moment. I wonder why. And so you plug 2 back in, y at x equals 2 is 2 squared minus 4 times 2, and that gives us that magic 4 minus 8 that we saw in that table before, where that's twice that size. Okay, and there's a reason for it. It's called completing the square. This is x minus 4. Okay, this is actually shorter, but I think I'll show it as longer. And so I can even off the sides, x minus 2 times x minus 2, right, which gives me x squared minus 4x plus 4. And I can subtract 4, and I have the same calculation, because this is x squared minus 4x. Okay, so evening off the sides, completing the square is what this is all about, but it also is hinged to the rates of each term. And when you get rates of change that are 0, where are the rates of change 0 on a curve like this? It's where it's flat. Well, I think I'm generating maximums and minimums. And that's what calculus is about. Calculus is about the rates of change. And we use y prime to talk about how things are changing. And that is changing according to that formula. And minus 4x is always going down at 4 to 1. And if I want to find a max or a min, I can set that to 0. And when does 2x equal 4? When x equals 2. So that's from a calculus standpoint. And then I could plug it back in. Now, I can't prove that's a minimum because, you know, we have 2 kinds of shapes, concave up and concave down. Well, let's look at, you know, at 2, I'm going up at 4 to 1. At 2, I'm going up at 4 to 1. Well, it turns out that we could do other numbers as well. So let's change this to a 3 by 3. Okay, so a 3 by 3 gets me 9. And if I put 3.001, 3.001, we'll keep 3 decimal place accuracy here. I get 9.06001. And I can see a 6-to-1 rate of change. If this had been a 4, and this had been a 4, well, that's 16, but this changes to 16.008001, and I'm going up at 8-to-1. At 2, I'm going up at 4-to-1. At 3, I'm going up at 6-to-1. At 4, I'm going up at 8-to-1. Wow, seems to me there's a pattern here. Well, let's look at it generically. All right, so I've got an x squared area, that's what we did over here, and I changed the dimension by 0.001. So I really went up a little bit, and I got to show that. It could have been more accurate if I had thrown more decimals. So if I had done over here, let's say 4.00001, then this is going to change to 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's even closer to 8-to-1. So mathematicians have decided to call this dx, that little change in dimension. And it's like framing that shape. I have a picture, I just put a frame around it, little, not on both sides, just increased the dimension, length and width, right? Height and width by the same amount. And I get a change. This one is x dx, it's a rectangle. This one's x dx, kind of hard to show it, x dx. And it seems like I've got an x dx and an x dx. And that's going to be my change in y. And what is y? Y is the area. X squared is the area. All right, so I'm getting a change. Little change in y, and it's this area here. All right, and that is hinged right there. And so if I add these together, if we generalize here, then we have 2x dx. And if I divide by dx, that's a change in x. x2 minus x1, small change. 0.001 or however small I want to make it. And I have a change in y, y2 minus y1. Bigger square minus littler square. And if I divide by dx, which is represented by x2 minus x1 up here, I get what's called a derivative. And so what's the rate of change of the quadratic? 2 times the x value. And so back over here to the last problem on lesson set 29, I said I'd get back to it. We're getting back to it. How would you graph this algebraically? You would say cup shape up. Cup shape up, okay? Minus b over 2a, positive 2, plug 2 in, minus 40 cut in half, minus 20 plus 7, minus 13. 0, plug 0 in. 0 gets us what? 0 gets us 7, and going down at 20-to-1 at that instant. Okay, and we can prove that over here with calculus or show it. We've done it with just numbers in the past. So let's do it with calculus. A of x equals 5x squared minus 20x plus 7. So a prime of x squared, we just said, changes by that formula. That's the rate of change. And this is representing the formula for rate of change. And I'm multiplying it times 5. Okay, and I know linear functions change at a constant rate, and constants don't change. So now I have 10x minus 20, and I want to know when my slope is 0. Sure looks like x is 2. Plug it back in, you get the negative 13. But let's get the double prime. Let's get a double prime. The rate of change of the rate of change appears to be 10-to-1. Why is it 10-to-1? Because I'm multiplying by 5. Used to be 2-to-1. Now it's 10-to-1. I could show that with some table values, but I don't see any reason at this stage to do that. And let's go back over here very quickly. And this is just part 1 of a conversation that nobody's going to be testing you on. Just showing you where you're headed. Nice to know where you're going in life. And I'm ending every one of these videos by putting another layer of change on that 2 by 2. That's my 3rd or 4th layer of change. And I'm using the marker as 2 units and half a marker as 1 more. And so I'm coloring in squares, a 2 by 2. Eventually, I'm going to show you all the area and how it changes as we go through the term. But that's enough right now. That's challenging enough to take in the conversation we just had. But we're going to repeat it and repeat it and repeat it because it doesn't take long. It doesn't take all that long, but it does take some effort. All right, so that's going to get uploaded, and it's a nice day out there. We're finally heading to spring, so I won't have to stay safe, warm, and cool for maybe another few days, but then it's going to be stay cool. Safe, but stay cool, especially when it gets up above 100 degrees. All right, toodaloo.